etc. Yeah, screen is visible.
Yes, sir.
Yes, sir.
So this is a spreadsheet, and this also same here. First it says you can put which bridge and where it is and whatever locations you want to put, and all cells in light blue only you can change, others you cannot change. Now it comes to first fixing linear waterway. So as per these CWC reports, if they are applicable, this will be the waterway. So from here you can put if they are applicable. Our case, they are not applicable, so we have not put it. Then as per Lacey's formula, it comes, sorry, here, how much design discharge I put, let me see. Oh, this was another example. Let me solve this example for you. This is for Godavari. Where is this case? Okay, anyway, we can see from this also, it does not matter, we can change in any case. So okay, let us do it again. So we will write here bridge, first whatever area description of this bridge in zone 1C in C division NCR, whatever we want to write, we can write. Location also, whatever you want to write, and design discharge. So our estimated design discharge was 730.20. So let us say we take it 740 or 730, whatever rounded off value you can take here. Now, as per this, if it is applicable, our zone is 1C, so none of them is applicable. Now it is calculated as per Lacey's formula, 131. Okay, and now just an example, because we don't, let us say the width covering all active channels is coming 110 meter, and from overall consideration it is coming around 120. So to start with, we will adopt 120 meter at the width here based on these two considerations. Then for rivers with rigid boundary, whatever I say, those considerations are written here. If that is the case, then this C will be applicable. You can write here. For river in sub-mountain region, if that is the case, you can write here. Now, based on all these consideration A, B, and C, if it comes 120 meter, then we will put it 120 meter here. Now, it comes to fixing the number and length of span. So, if it is navigation channel, any requirement, that is not there. RSI also we have not done in this case as per that if some span restriction. Now let us say number of span. For number of span, first we have to decide what sort of spans we are going to use. Now this is one of the most commonly used RDSO span, 100 feet PSC girder. Its overall length is 32 meter. So for our case, it is 120 meter. So we will need around 5 spans. So let us say we give 5 spans, and here let us say we calculate the economy of using 5, 6 or 7 spans, all three spans. Now number of piers it will calculate automatically. Now we have to go to unit cost of pier and foundation. Now this have given some value, there will be actual value. It will calculate total cost of pier. Then you give unit cost of abutment and foundation. There will be 2 abutment, it will calculate. Superstructure cost, we have given unit cost. Okay, and then total cost. We can take superstructure same also, because let us say we are going to use same span. Then now you can see the overall 5 is coming minimum here. So we will say based on this we have taken span as 5. So here you will need overall span at 24, and up to here the nearest span length, this 100 feet, is 32. So you need 24, 32, so far okay. And gross waterway being provided is this. Now we will calculate the adequacy of waterway. For that we will need the depth. So width of waterway just upstream will be your gross waterway. Now depth of water, if you got stage discharge relationship, from there you put it. In this case, let us say we don't have, so you assume some water depth. Let us say I assume 2.1 meter. Just to give you an example. So it will give you area of waterway at this location. If this is assuming it to be rectangular, if it is not rectangular, you want to take some other shape, give that value here as per your shape. Then, so based on D or E, whatever it is, how much is your waterway coming? 345.303. Give it here. It calculates velocity of water just upstream of your bridge, 2.143. Now coming to Manning's formula, first you need slope. So for slope, distance on upstream, how much distance you have taken the level and what is the level? Downstream, at what distance you have taken the level and the level. With that it will calculate the slope. Roughness coefficient, this is the table depending on your river condition. So I have taken natural channel in fairly good condition, so 0.03. Then assuming it to be rectangular, it has calculated the weighted perimeter. If it is not rectangular, you want to give some other, like for triangular I have calculated, or whatever you give that value, calculate from your value. And now based on this J and K, what value you are giving is this 168.63. So now velocity of water, number one, it is becoming more, 3.1, and here in from first consideration it was coming 2.1. So we have to increase this value and we have to decrease that value. So you keep on changing the depth of water. Let us say I change depth of water to 2.2 meters. Just to give you an example. So this value will become 361.746. Now velocity of water is reducing. So it means I have to decrease it. I have to increase this value. So take 1.9 rather than this. So this value is 312.417. I got value of 2.369. It has increased, and here also this will become 168.23, 2.9. So now gap has narrowed down, 2.4, 2.9. Keep on doing this. Let us say I take 1.6 meter till you get same value, almost same value. Same value means need not be exactly same to the decimals. Almost same value. Now this has become 2.8 for 1.6 meter depth, and let us say how much this becomes 0.63. It become 2.6. Like that you keep on doing this till you get the same value. Okay, take 1.4 this time. Now what happens? This value becomes 230.202. 215. It has gone quite high, so we have to take 1.5. With 1.5 it becomes 246.645. This value has become almost 3, and this value 167.43. This now become has less, so maybe we have to go to 1.55. Like that, keep on doing this iteration till I'm not spending much of time here because we have got less time. Like that, some value, whatever depth you assume, let us say we take at 1.55. 1.55 kitna aa raha hai? We'll see. It's coming 2.9 here, and it is coming 167.5. So you can further reduce, maybe go 1.5, whatever it is. You will calculate the velocity. Now, if this velocity is coming more than 3 meter per second, which in this case it is not coming, in that case you have to go again and increase the number of span here, and you have to keep on increasing it till both your velocities they match and they become less than 3 meter per second. So this your span arrangement is finalized. Now our depth of water we have taken 1.55. So this pier we have to say first step, how much is in water. Let us say its width is 4.5 meter and height is 1 meter, this H1. Second, sorry, this bottom one 4.5, top one 3.5. So height of water will be only 0.55. Total was 1.55, and other, if there are 3 projections, you can put 3 or 4. So here this is submerged mean width, and based on that, the effective waterway now after this is 131. And what was our requirement? Our requirement was 120. So it means we are providing more than that waterway. So this waterway is sufficient. Otherwise, again, you can change. Then go to scour depth. In scour depth also, first the catchment area. So our case catchment area is 162.080. So increase as per this up to 500, you have to increase by 30%. No, sorry, catchment area. Yeah, it was 162. So up to 500, 30%. 30% increase by 30%. This is QF. Then you give whether Lacey formula you want to calculate or other. So let us say we want to calculate from Lacey's formula. Particle size is 1.5. It calculates silt factor. Now there are 2. If your waterway provided is not less than Lacey's width, means more or less. So it calculates for both the cases. Our case it is more. So this will be the applicable value 3.615. So 3.615 here. With that, it will multiply with all factors and all, and it will give you for abutment 4.519 and piers 7.23. These are for fleshy rivers, for clay bed and all, if that is the case. And based on all these conditions, finally, in our case, it is coming 4.519 and 7.230. This is what it is coming. So we have calculated this, and below that, whatever is 1.75 or 1/3, you add that. That will be your founding depth. So all calculations, and you don't forget any of those requirements. This sheet I have copied. You put your own data and try with this. Similarly, for afflux, it has already calculated velocity and everything, and it says afflux is 0.28. Now, do you want to give any reduced value? Let us say you want to give 0.25. You do little bit less than that, can be maximum value. So based on this 0.28 and 0.25, how much you want to take? 0.25. We will take lower one. And requirement of clearance, again, it depends on design discharge. Our design discharge in this case was 730. For 730, clearance is 1500 from here. So you will need 1500. 1500 mm clearance you will need. If pipe or siphon, you will need 0. Then do you need any relaxations, or have you taken any relaxation? No, in this case. From navigational point of view also, sometime your clearance may be decided. That is also not there. So from all considerations, sorry, this is in meter. I have written in mm. This is in 1.5 meter. So from all these considerations, your clearance required comes 1.5 meter. Now, what is the bed level of river at this level? We have to check 604 point this. So your calculated HFL bed level plus afflux plus whatever afflux, sorry, is comes 609, and sorry, calculated 606. Actual, let us say at site you have observed 609. So your HFL to be adopted will be higher of this 609. Add clearance is in that 610.5. So your bottom of superstructure has to be kept above this level. That's all. In this case, we have kept at 612 meter. That's why it has given okay. Let us say if I give 610 meter here, see what will happen. It is said not okay. So it will automatically check. Similarly, depth of construction of superstructure for this girder, it is given in RDSO drawing. It is 2.5 meter. So your top of superstructure will be bottom of superstructure plus this. So 16.4, and we give freeboard clearance as 1. So you will require your approach embankment to be at minimum 610. If your approach embankment is not at this level, it will come not okay. That's all. So very simple spreadsheet. You can use it and just calculate all those things without missing anything. That is what it was. Okay. Right?
Yes, sir. Yes, sir.
Now we will go to our subject, which was we are a bit late, but anyway, we'll start it today. Foundations, bridge foundations. So there are three: open foundations, pile foundations, and well, we will cover all these three in next classes. So first we will talk about open foundations, or what we also call as shallow foundations. Now you are all fresh from colleges. Can you tell what is open foundation? What is the definition of open foundation?
सर सभी मतलब कई इंजीनियर्स ने अलग अलग वो दी थी सर मेनली जो फॉलो होती है सर उसमें ये बताया गया कि L by B रेशियो जो है सर वो सॉरी D by B रेशियो इट इज लेस देन 1.
Any other definition? There is a standard definition which is given by IES code. IES 1904 is the code on foundation. It defines shallow foundation.
सर ये साइड से कोई रेजिस्टेंस भी डेवलप नहीं करती है, ये सब खाली बेस रेजिस्टेंस डेवलप करती है सर.
बेस रेजिस्टेंस तो आपका एंड बियरिंग पाइल भी करता है नहीं, बट दैट इज नॉट कॉल्ड shallow foundation. There is a very small and very technical definition of shallow foundation, which will be useful for us when we go to calculation of bearing capacity and all. Anybody else? Any other guess like to take? What is called shallow foundation?
The depth of a foundation upon width is less than 1.
वो तो है, that is it can be even 1.1 also.
So the significance of overburden pressure over the foundation.
This is the definition as per IS code. A foundation in which load transfer is primarily through shear resistance of bearing strata. So this is your foundation. Why I'm telling you this? Because you will use this. This is your foundation, and the load transfer from here to this is through shear. Then it forms what you call that, Tarjagi's classical bearing capacity failure. Like this, when this load comes, the bearing capacity of this decides load transfer, and then shear zones are developed or not developed, and there are different forms of this. So this type of foundation where this mechanism is taken into account for calculating its behavior and all is shallow foundation. So it is those foundation where load transfer is primarily through shear resistance of the bearing strata. Based on shear strength only, its shearing resistance, you get the bearing capacity mainly. Whereas in deep foundation, it can be either the point resistance, which is end bearing, or it can be shaft resistance, side friction also. In this, it is basically shear failure or a variety of shear failure, and that gives you the bearing capacity. So this type of foundations are called shallow. This is important. We will see when we go further. We use this for calculating their capacities. ठीक है?
Yes, sir.
That is the definition given in
Yes,
IS.
sir.
But as you rightly said, there are so many other definitions also. Yes, there are so many other definitions. We will see them maybe as we go. But this is what is the definition which IS code gives. So these foundations can be of different types, or they are. One is called spread or ped footing. This is basically their length oblique width ratio. Depending on that, you define them. Either it is when it is small, length oblique width ratio is small, you call them spread footing. So here, as you know, the load comes, then there will be a pier or something, and then there is a spread footing, individual footing or isolated footing, and that transmits the load down to the bearing strata. Second type of this is known as strip footing. In this, your length L by B ratio is quite high. So load is a longer load rather than point load. Some load is coming from here. You may not have separate pier also in most of the cases. You may or may not have. And then you have a foundation here. Then you also have what is known as mat or raft. When too many columns closely spaced are there, then rather than giving individual spread footing, it is found economical to rest them on a common mat or raft. So this type of footings are raft or mat footing, and you can have circular raft also with annular shape. If your loads are in a circle, you can be like ring, like your inch tank and all, the most common thing, or your structure also may be like that. Then you have a annular raft. It is ring and cell footing. This type of footing are ring and cell footing. So they are various types of shallow or open footing. I'm not going into detail because you are all fresh from colleges. Another type of footing is known as deep foundations, where your bearing capacity or the capacity of the strata to take the load at shallow depth is not adequate. Then you go for deep footings, and they are used to transmit the loads to deeper load bearing strata when bearing strata of adequate capacity does not exist at shallow depth. At shallow depth, whatever is your load and whatever is required load bearing capacity you are not getting, then one of the choice, or most of the time the choice is you go deeper, and there your transfer of load is through end bearing resistance or skin friction or both. It can be point resistance at the tip of your bottom of your foundation, or it can be through skin friction around the shaft of the foundation, or it can be combination of the both. And these are most common type of deep foundation, pile foundation. So in case of pile foundation, you will always have a structure, of course, then a pile cap on all these piles, and below that there will be piles, they go to deeper strata. So this is pile foundation. These type of foundations are known as well foundation. Here again, load is coming through this pier or whatever you call. Then you have well cap, and then you have a well, which is a hollow structure below that. We will see other components of well when we go into well foundation. But basically, rather than having individual slender piles, you have a massive well structure below that. So they are well foundation. And third type of foundation, which can be taken as a offshoot of well foundation, is the caissons. Right? Well, normally they are cast at the site and then they are sink. Whereas caissons, this well is casted somewhere else, sometime, most of the time. Then it is brought to the site and then they are sunk. So caissons, only sinking is done at a site. Most of the fabrication or casting, depending on it is steel or masonry or concrete, is done outside. Then caisson is floated to your required location, and then sinking is done. So these three are most common type of deep foundation: pile foundation, well foundation, and caissons. Okay, ठीक है ना?
Yes, sir.
Yes, sir.
Now, first we will see, this question comes first in railways कि हमें किस टाइप की फाउंडेशन कहाँ अडॉप्ट करनी चाहिए, which type of foundation should be adopted where. So these are the general things which are covered in a B&S report also, and technically also. Shallow and open foundation, number one, they are suitable for non-erodible strata. नंबर वन, यदि स्ट्रेटा एरोडेबल है, आपने ऊपर रखा, एरोड हो जाएगा, फाउंडेशन लटक जाएगी हवा में. Another thing is where you have got adequate safe bearing capacity at shallow depth of maybe 3 or 4 meter, up to 3-4 meter depth, you can get a strata having required safe bearing capacity as compared to your load. Then these foundations can be suitable. जैसे अक्सर minor bridges में, box में, in cases में we go for shallow foundations. Here also, generally you adopt isolated footings when your safe bearing capacity is about 150 kilonewton per square meter or more, 15 ton per square meter or more. And normally when your bearing capacity is lesser, in the range of 10, then you have to go for raft. That is another. They are only guiding principle, not very hard and fast. 150 may become 140 also and 160 also. And another aspect, when you put them on the rock, when you put these foundations, shallow foundations on rock, you do some keying of foundation of rocky strata. Let us say this is your rock. You just don't left it over this. You do some sort of chiseling for some depth in the rock and then put your foundation there. So this keying in is about 0.3 meter is good enough for hard rock, and you may need to go up to 1.5 meter for soft or heavily disjointed rock. And this is subject to codal provisions. Various codes also, they define various things. We will see this, what does our code say. And wherever you got sloping rock, let us say this is your sloping rock, you normally do benching in this and then put your foundation. Or if your foundation is large in size, then in rock you do benching like this and then put your foundation also like this. So it must be suitably keyed in the rock, whatever is below. And they should be protected against undermining by suitable aprons and cut-off wall, including launching apron, both on upstream and downstream side. Let us say I am putting a box here. This happens many times in the box. I put the box here. This is my river. So I have to go below river bed as per that scour consideration and put box at the whatever is maximum anticipated scour level. In addition to that, you also put some arrangement like cut-off wall, toe wall, and you put some launching apron here, depending on how erodible your strata is there. So that if there is an erosion, this launching apron will launch and it will prevent further erosion. And this cut-off wall and toe wall also you give to avoid their erosion. So this is another important suitable erosion protection measures should be taken against in case of shallow or open foundation. Many times, especially in boxes, previously, I'm telling 5-10 years back or maybe more than that, box is easy to cast, easy to construct and बड़ा आसान होता है. Contract management भी उसका है, concrete का item pay करना है safe. So there is a tendency for people to cast box. Box is a good structure. You can have reduced clearance also. But in some aspects it is very bad. I know of one section which was with me, Karur Dindigal in Southern Railway, where a new line was built and we took over. Otherwise it was a dry area, but there were very heavy rains during that year and there were erosion. So if you see along the track, this was rail, then sleeper, below that some ballast and track, and this box was hanging from this, below this nothing is there. Around 8-10 such boxes were hanging. Kuch to gir gaye, some have fallen, some were hanging with something like this, some support here, there and all. Because number one, whenever you cast a box, when will you cast? Most you will cast in dry season, when there is no flow. And if you see, let us say this is my bed level. What you are seeing in effect is silted up bed level. In dry condition, you will have silted up bed level. Your actual bed level will be somewhere here. You can easily find it if you start excavating with some fauda or hand. You will find suddenly there is change of resistance in your digging resistance. This silted up soil with hand you can remove, but when natural this thing bed will come. But we people considering this as natural bed level box, यहीं बैठा दिया, नीचे तो जाना और दूर था, ये तो immediately erode हो जाएगा. So that's why whenever you are putting shallow foundations, especially in the errata strata which is likely to erode, please be very careful to take suitable anti-scour measures and found it at the correct location using that scour depth calculation. Very important. Otherwise ये बहुत बार होता है, वो erode हो गया और नीचे बैठ गया जाके. And we always put a lean concrete footing. These footings should rest on a lean concrete bed of adequate thickness. You always give a lean concrete base below that, below these footings. They directly don't rest on your strata. So these are some of the features and where we can use shallow or open foundations and what precautions we must adopt. Coming to pile foundations, of course, they are used when the soil below bed level is weak, whether pile or well, both. And they are also used, number one, it may be weak, so it may fail. Sometime, even though your soil is able to take that load, but its settlement, you know, in case of foundation, we will see this as we go to open foundations. Whenever you design open foundations, you check two things. It's adequacy of bearing capacity and the settlement. Both should be within the limits. So sometimes your bearing capacity is okay, but your settlement is unacceptable. And in that case, it becomes necessary for you to do pile foundation or deep foundation. And these pile foundations, nowadays you will find at 99 or 99.5% bridges, wherever you might have gone in the field, except very, very rare, very wide and rivers carrying heavy flow, normally people go for pile foundation. Their biggest advantage of pile foundation is their construction is very, very fast. Construction is very fast as compared to well. Well takes 2-3 years to sink. Second thing is, if one pile gets defective or gets stuck up, you can rectify the situation by putting another pile. Let us say, take an example. You have designed 4 piles and over that pile cap like this. Now, in this pile, your chisel or baler got stuck up, it got buried, or you could not go below, something happened. No problem. You can design another pile here and maybe you can change shape of your pile cap. Redesign can be done quickly and you can salvage the situation. Whereas in case of well, if your well gets stuck up, you are finished for months together. Rectify, we will see when we go to well foundation. So that flexibility is not there, and well takes very, very long time for sinking. So it is, nowadays everybody is in a hurry, instant coffee, instant tea, everything instant. So in the instant days, piles have become very popular, but they are generally suited for construction in deep standing water where scour is moderate. If your scour depth, let us say you have designed a pile like this and this is your bed level. If your scour depth is very high, then in your design you will take this as freestanding pile. And if this height of pile becomes very long, very tall, your pile may become uneconomical. You may need very heavy pile. It may be costly also. So because it is a slender section, your L by H ratio sort of thing, that buckling comes into picture. Whereas normally most of the forces, most of the times you design your foundation for compression. Of course, you check for others, but compression is your main this thing. And second thing, in rivers where some heavy objects or some heavy boulders or heavy maybe tree trunks are likely to come and hit your bridge, you don't provide piles because it can damage the pile. Whereas well is a very sturdy component, it may not damage the wells. So that is another consideration, pile versus well. But as I told you, their construction is generally faster. That's why they have become very popular. Commonly available machinery everywhere. People, well does not need very sophisticated equipment, let me tell you, but that expertise is limited in the people. Very few people are there who can do the well, whereas pile, nowadays every Tom, Dick and Harry will do the pile. Another thing is they are not very suitable when liquefaction of soil is expected in case of seismic activity. Yeah. Now what we have to check them piles for liquefaction in zone 4 and 5. You must be knowing India is divided into 4 seismic zone, 2, 3, 4 and 5. In seismic zone 5, if this is your deepest cover level, you can check them for liquefaction. And if it liquefies, then this frictional resistance is not considered. In that case, your pile becomes freestanding pile, depending only on tip resistance, and it becomes very uneconomical. So in high seismic zone also, sometime your pile may not be suitable. Quality of concreting is very critical in piles. It is a very slender element and you have to mostly work underwater. You have to work mostly in black hole. Where your concrete is going, you are not able to see, and therefore you are not able to visually examine anything, and therefore you must be very, very good in concreting when you use piles. So where you can do good quality of concreting, better you must do RMC or pump concrete rather, not RMC. You must, of course it is not must, but I am of this opinion that for piles we must invariably do pump concreting. Whatever places where I have done piles or where I designed also, I used to write, maybe I may be exceeding my brief, that we must use pump concreting. Because if you are able to pump the concrete, it is a simple test. So many of its ill effects can be taken care of. Segregation, proper mixing, You don't require much of hardly any compaction if it is pumpable. So if you can pump a concrete, it gives you an indirect assurance that your concrete is of good quality. In fact, I am of the view we should ban other than pump concrete for bridges. We must use only pump concrete, because if you pump the concrete, it tells you so many things, that so many things have indirectly been taken into account: consistency, all other things, bleeding, all those things are obviously eliminated only by using pump concreting rather than normal concreting. So whereas in well, you see in front of your eyes, first it is cast and then sunk, and you need not have very sophisticated methods of concreting. These are the some of the features or advantages or things which decides your choice whether you want to go for pile or well. In well,
Excuse me, sir.
yes, yes.
Sir, in addition to pump concreting, can't we individually analyze all the piles using NDT methods like pulse echo?
We do it. I will tell you when we go to pile foundation, we do it. There are high integrity supersonic tests. Nowadays, there is something called cross hole ultrasonic measurement, CHUM tests and all, where you put cameras and all. But in spite of everything, the fact remains that we dump or we pour our concrete in an area which we are not seeing visually. So some sort of element of uncertainty all we can improve upon. Yes, as you rightly said, and many improvements have been done. As when we go to pile, I will tell you. But still, it is not like well or open foundation where everything is done in front of your eyes. And if anything wrong goes, you are able to observe it. So that way, we are always at a disadvantage in case of piles. Okay.
Yes, sir.
Right. Wells, generally when depth becomes more than 25-30 meter, well will be economical. So rivers with high scour depth or very heavy structures are, and of course India is the country where maximum well foundations have been done. You call it Yamuna Bridge or you call any old structure, you see the Taj Mahal or you do Lal Killa and all those things, they are all on well foundations. So in India is country where maximum development of technology regarding well has taken place, and more than this depth, piles normally they become uneconomical. And these wells, by their sheer size, their total load carrying capacity in both vertical as well as horizontal direction is much high. In pile, you can still improve the vertical load carrying capacity, but their horizontal or lateral load carrying capacity is a suspect. That's why nowadays there is a concept of bigger dia pile. You are putting piles of dia 2 meter and 3 meter. People have used recently in Indian Railway or not, but in many places. So you are trying to combine the advantage of pile and well both in those cases. Well has got very, very high vertical and lateral load carrying capacity, and it provides a very good grip when it is taken sufficiently below, and therefore it is most suited for river bed subjected to heavy scour, because it gives you side resistance, it gives you end resistance, very massive. So they are highly suitable in very large river. That's why you see all the bridges in river Ganga, on river Yamuna, Yamuna, you see on Brahmaputra, you see on Godavari, third Godavari bridge, even first, second. Most of these iconic bridges or bigger bridges, they are on well foundations because of that reason. And their advantage is they can be constructed through granular as well as cohesive soil both. Whereas pile is through cohesive soil, maybe if your end bearing point, you get very deep. Sometimes it is very difficult to design pile foundation. If you are putting pile and because of cohesive soil here, especially if it is failing in liquefaction or something, you are not getting good result. You will need some strata with very good, either rocky strata or strata with very high N value or end bearing resistance, say N value of the typically order 60, 70, 80 like that. And if you are not getting that, then it may become uneconomical. Whereas well can be constructed through any type of strata. Well can also be taken through soil having boulders, logs of wood or such type of obstruction. If some obstruction comes, small obstructions through well, you can easily remove it during well sinking. Big obstruction of course takes time, but still remove. Pile, your dia itself is 1 to 1.5 meter. This is the dia which you are using. And during drying, if here one maybe 0.3, 0.4 meter boulder also comes, you will mostly get stuck up. You will not be able to break this. It requires very heavy efforts to go through it. So that is the advantage. And you generally adopt circular well for single track bridge. If you adopt circular well, normally for single one line, and generally circular well is constructed for a dia up to 9 meter. More than 9 meter, you don't construct in railway. I'm telling circular well, where you need more width. Let us say there are 2 lines or something. Then what you adopt is double D well. We'll see what is double D well, like this. So they are most common for piers and abutments which are wide to be accommodated on circular well. So these are some of the features of well foundation. Now we will see some terminology which we will use mainly in context of open foundation, but maybe in other foundations also. And this terminology also is from substructure code. First terminology is gross pressure intensity. What is gross pressure intensity? If this is my footing, I'm talking about open footing. This is my ground level. Then some superimposed load is coming. Let us say this is live load or superimposed load. Then there is dead load of this footing. Let us say that is PD. So here PS plus PD divided by whatever by width, that will be 1. In addition to that, you take weight of this earth fill also, say PQ. So you will add plus PQ times B also here. So this is your gross pressure intensity here that we call Q. So it is total pressure at the base of footing due to weight of superstructure, self weight of footing and weight of earth fill. Gross pressure intensity. Simple. At this level, how much pressure my strata at that level is subject to, that is Q. Another term is net pressure intensity. Here you reduce the weight equal to earth fill. The logic is this. This is my ground level, and at this level, before construction of my footing also, if this is my depth D and this soil has got its unit weight gamma, then pressure intensity of gamma D was already acting here and it was in equilibrium. So how much I have increased? Finally, after constructing of this my footing, it is Q. So the increase is Q minus sigma, this sigma. That is called net pressure intensity, Qn, the intensity by which I have increased the pressure at the bottom of foundation. So the excess pressure or difference in intensities of gross pressure after the construction of structure. This is the additional load which has come at the founding depth. We call it net pressure intensity. Then there is a term called ultimate bearing capacity, QF, as the word F means failure. This is minimum gross pressure intensity at the base of foundation at which soil fails in shear. That's why I said we are talking in context of open foundation more. And in open foundation, we said failure is always by shear failure. We'll see briefly as we go. Failure is always by shear failure. And when your soil has failed in shear, that of course gives your bearing capacity. That minimum pressure intensity, above that load in any case it will fail. That load or pressure intensity, kilonewton per square meter or ton per square meter, is called ultimate bearing capacity, QF. Then there is net ultimate, simple, QF minus sigma, QF minus gamma D. This is net ultimate, this is ultimate, this is net ultimate. So minimum net pressure at the bottom or base of foundation which will make the soil to fail in shear is net ultimate. So QNF, Q, QN, QF, QNF. These are the notations. And there is another term called net safe bearing capacity. Now, in any structure, we always apply a factor of safety to have extra margin against failure. So the net ultimate bearing capacity, QNF, divided by factor of safety is called net safe bearing capacity, and normally for soils you take factor of safety equal to 2.5. So this is QNS, net safe. And from this you want to go to safe bearing capacity, net safe and safe, add QD in this. QNS plus gamma D, that will be safe bearing capacity, QS. So it will be QNF divided by F plus gamma D. Various jugglery, please be very careful what terminology we are using and what is what. So net safe and safe. There is another which is known as safe bearing pressure from settlement point of view. All this whatever we are seeing above up to F so far were from shear failure or bearing capacity point of view. Now we will see net from safe bearing pressure point of, from settlement point of view. So the maximum allowable pressure to which the foundation may be subjected without producing excessive settlement. Now this settlement generally we take 25 mm total, but it depends on what type of structure it is, and there is a concept of angular settlement also. We'll see as we go to open foundation. Somewhere I will tell you. You can increase this also depending on how is your structure, how sensitive your structure, how much is total. But normally by default we say settlement of 25 mm or excessive differential settlement. So that pressure is called safe pressure from specified settlement point of view. And finally there is something called allowable bearing capacity. Let me tell you, many times in drawings and all you use word safe bearing capacity, but actually what is meant there is allowable bearing pressure. Please always be very clear about this. And allowable bearing pressure is lesser of the two. Two means your net safe bearing capacity, QNS, and your safe bearing pressure from specified settlement. Lesser of the two value will be your allowable bearing pressure. So whenever we use bearing capacity, we use that term ecologically. Soil की bearing capacity इतनी है. It does not have any meaning. It is always in relation to the structure which is standing on that, because it varies on. We'll see. अभी हम देखेंगे open foundation में जब हम term use करते हैं, it does not mean anything. हम कहते हैं sand इसकी soil की हिसाब 10 है. 10 generally है. It will vary on, यदि structure की width ज़्यादा है तो ज़्यादा हो जाएगी, width कम है तो कम हो जाएगी. Depends on so many bottom of your pier, उस पे depend करता है, and how much settlement you permit. Actually, what we mean by bearing capacity is allowable bearing pressure. Always be very clear about this. And it is less of net safe bearing capacity and safe bearing pressure from settlement point of view. Okay, ठीक है ये?
Yes, sir.
These various jargons, what is ultimate and what is safe, what is not safe. So when we say, आप भी जब फील्ड में जाएंगे एज एन, आपको कोई भी स्ट्रक्चर कंस्ट्रक्ट करना है, आपके पास एक हेडक्वार्टर से ड्राइंग आएगी, उसमें नीचे लिखेगा इट इज अज्यूम्ड दैट सेफ बियरिंग कैपेसिटी एट बॉटम ऑफ फुटिंग इज 10 टन पर स्क्वायर मीटर. प्लीज बी वेरी क्लियर, ही इज टॉकिंग अबाउट दिस, इवन दो लिखा उसमें सेफ बियरिंग कैपेसिटी होता है. So be very clear what is required. ये बहुत कंफ्यूजन होता है लोगों को फील्ड में. हम एक प्लेट लोड टेस्ट से सेफ बियरिंग कैपेसिटी निकाल लेते हैं. We assume that no, उस पे प्रोसेसिंग करनी है. कैसे करनी है? I will tell you. You have to do some processing and then only you will get safe bearing, which actually we mean allowable bearing pressure. वहाँ यदि उससे ज्यादा प्रेशर आ गया या तो आपका फेलियर हो जाएगा, अदरवाइज आपका सेटलमेंट आपके लिमिट से ज्यादा हो जाएगा. सो आइदर यू विल हैव लिमिट स्टेट ऑफ फेलियर और लिमिट स्टेट ऑफ सर्विसेबिलिटी इन सेटलमेंट. नाउ वी विल सी सम फ्यू प्रोविजंस ऑफ सबस्ट्रक्चर कोड regarding open foundations. Now we are talking about open foundations mainly, pile and well we'll see. So first is clause 6.1 of substructure code. It gives general design criteria. General design criteria. What it says, following basic requirements should be fulfilled. In case of foundations, for open foundations, these should be fulfilled, and it is for bridge, of course. As far as possible, the foundation should be located on firm ground having stable strata. It means filled up soil में इस टाइप की सॉइल में अवॉइड करना चाहिए एज फार एज पॉसिबल. इट मे नॉट बी ऑलवेज पॉसिबल, but as far as possible, try to put open foundation on a farm. And foundation shall normally not rest on compressible soil. It can be filled up soil. By nature, it is compressible soil, highly plastic soil. Normally, you should not rest there. If that is not possible, as I told you, may not be possible, then you must design the foundation adequately against any expected failure. What it means? Not only bearing capacity, please take care of your settlements and differential settlements also. Be very careful about that. If your foundation is resting on compressible strata. And another thing it says is, if you see in the plan, this is your bottom of your foundation. If you divide it in 1/3, 1/3, 1/3, first 1/3, second 1/3, and third 1/3, then it says the resultant of all the forces. If this is your foundation, and here you will have vertical force, you will have horizontal force, so there will be resultant force which will be inclined like this, and it will hit your foundation, not a rather bottom, we always say here. So it says resultant of all the forces on the base of foundation for rectangular foundation shall fall within the middle third if structure is founded on soil. If it is not rock, let us say it is soil, then this resultant force should hit somewhere here. Or otherwise, what you can say, sometime we also say, RE wall में जब जाएंगे तब आपको बताएंगे, if this width is, let us say D or B, to avoid confusion, D we use what? If this is B, this will be B by 3, this will be B by 3, this will be B by 3, and this is your center of foundation. So your maximum eccentricity, which will be measured from here, can be either this or this, or indirectly it is said eccentricity should not be more than B by 6. That is what it means. Your resultant of all the forces should hit in the middle third, or indirectly you can say your eccentricity should not be more than B by 6 for rectangular foundation. Why it should not be there? Any idea? Anybody can tell?
The stability
To avoid tension, sir. So to avoid tension.
Yes, to avoid tension, exactly. If eccentricity is too much and you analyze it, you will find that if this is compression, you have got tension in a significant amount, and soil cannot take any tension. Its tensile strength is 0. Rock still can take some tension. Soil cannot take any tension. You want to avoid the tension. That's why you don't want. And you must be remembering what is called Meyerhof formula, where if eccentricity is E, then you only considered B minus 2E as the area on which your total force will be acting. You two times eccentricity you neglect, and your compressive force is supposed to be acting on B minus 2E only. ठीक है ना? Correct? ऐसा ही होता है ना? Because I have read this maybe 30 years or more. I have become old fellow. I have forgotten. You are fresh people, so you must correct me wherever I am wrong. Okay. Now another thing which our code talks is safety against strength failure. So it says there should be no bearing capacity failure. First thing. So open foundation, we must check for bearing capacity, and then it says for initial design or preliminary design, or for design of smaller structure which are not important, it says the so-called safe bearing capacity means considering only bearing capacity point of view, not from settlement point of view. The safe bearing capacity, it says you can assume from the values which are given in table 6 of substructure code, and this is how table 6 looks like. Presumptive safe bearing capacity of soil. Please read word very carefully. Many time हमारे यहाँ रेलवे में भी लोग इसी को सब they consider this as the final gospel truth and take this. Please read. First code says this is for what, and then word itself is presumptive, and further also it is said. I will show you. Here it divides into rock, soil, and all. So first it says rocks, Then various rock, hard rock without lamination, laminated rocks, residual deposits, soft rocks. For that it gives safe bearing capacity in kilonewton per square meter, and inside bracket is ton per square meter for rocks. Then it says for non-cohesive soil, again gravel, sand, gravel, compact and all, these are the value. Note, we will see what is the note. Porous sand, compact and dry, this much. Dry means ground water table is at a depth not less than width of foundation. This also we'll see in the notes what is meant by dry. Medium sand, compact and dry. Fine sand, dry lumps easily pulverized by finger. Loose gravel sand, fine sand, various type of granular soils, non-cohesive soils. Then cohesive soils, soft shale or stiff clay in deep dry bed, medium clay, which can be indented with thumbnail, moist clay, all various descriptions are there. For them, these are the values. And for peat and made up ground, these values are not given because it says these are the compressible soils and generally we should avoid resting our foundation there. And then these notes are very important to be read in this table. Normally, not only this, I will tell you, whenever you see any information in tabular form, please always read the notes and footnotes. Sometimes the whole scene changes by notes and footnotes. So not reading that can create a lot of problem. So number one, it says not one, values listed in table are from sheer consideration only. It has not taken settlement into account. That's why it is safe bearing capacity. It is not allowable bearing capacity, number one. Second thing, it says these values are rough due to this effect of characteristics of foundation, that is effect of depth, width, safe, roughness has not been considered. Effect of range of soil property, that is your phi value, C value, water table density has not been considered. Effect of eccentricity and inclination of load has not been considered. So it is assumed that it will be within eccentricity will be maximum subjected to d/6. And then it says for non-cohesive soils, that is sandy or gravelly soil, the values listed in above table shall be reduced by 50% if water table is above or near the base of footing. So if this is my footing and this is base of footing, if water table is likely to come here or above, I must reduce them straight away by 50%. See, it becomes half. That's why I said always read the footnotes, which normally we are not in habit. Table mein liya, tak se dala aur chal diya. Second thing, some place it was written compact, loose and all. What is meant by that? That it says the compactness of non-cohesive soils may be determined by cone penetration test, driving the cone of 65 mm dia and 60° apex angle. This is standard cone penetration test size. Power of 65 kg falling from 75 cm. This is used in means cone penetration test, dynamic cone penetration test. And if corrected number of blows for 30 cm penetration are less than 10, soil is called loose. If this N value in cone penetration test, which we call NCD, N cone by dynamic method, if NCD is between 10 and 30, it is called medium. And if NCT is more than 30, the soil called dense. So this is how it defines what is dense, what is other thing. Okay. And probably this last slide we'll take and then we'll start tomorrow. First part, against bearing capacity failure or shear failure, the classical shear failure demonstrated by Tarjagi. And then safety against deformation and differential settlement. For that, whatever code says, the total and differential settlements to be within specified limit, and these limits depend on type of structure and substrate. There cannot be one limit for all. It will depend on type of structure. You are building a small baby culvert, you will take less value. You are building a Chenab bridge, you will take very stringent value, something like that. And then it says, for simply supported bridges, settlement shall normally not exceed 25 mm after end of construction. So after construction, up to construction, whatever settlement has taken place, that is dead load settlement. Neglecting that, the live load settlement, this is what it means. If you read it clearly, it means that live load settlement, dead load settlement has already been accounted into construction. That should not be more than 25 mm. You calculate the settlement for live load or after construction, whatever loads. After construction only live load will come, or maybe earthquake load or something, those sort of things. then it should not be more than 25 mm. And it says you can allow more settlement also if adjustment of level of girders is possible. See, very nicely. This is, let us say, your abutment. These are your piers, and you have put your girders like this, and this is your approach track. Now, if it sinks, what will happen? Approach will remain same and bridge will come here. So to avoid formation of these sags and all, if it says if adjustment of level of girders is possible in simply supported span, it may be possible by constructing some pad or something or whatever type of span, then that much extra settlement in vertical you can allow. So depending on what type of structure, what is its weight and handling thing, you can decide. And in case of structures which are sensitive to differential settlement, the tolerable settlement limit has to be fixed based on condition in each case. Some structures, they are highly sensitive to differential settlement. Can somebody tell what sort of structures they can be? Which structure will be highly sensitive to differential settlement? Any 2-3 type of things? Can somebody?
Masonry structures like arches.
One is arches. Yes, in arches you will develop crack or masonry. Second thing is fixed. We were talking about fixed and simply supported span. In simply supported span, even if let us say this span goes down, maybe there will be little bit redistribution load. But imagine in a fixed structure, this structure goes down. You know, the whole moment shear force, everything changes, isn't it? In fixed beam, if you change the level, your whole moment, shear force, everything will change. Fixed structures or very tall structures, cable stayed bridge, your swing bridge, not swing bridge, what you call suspension bridge, cable stayed bridge, those sort of very tall, where your structure is very tall, even a small differential settlement will result into a lot of shift. So that sort of thing. A tall structure, even in substructure also, if your pile is very tall or your wide is, your well is very wide, then you reduce the differential settlement limits there, because then the total shift will become very high, theta multiplied by whatever the base or whatever value you take. So those structures, you may have to fix your differential settlement and even total settlement limits on little bit on lesser side. So this is what code says. It says check it from shear failure or bearing capacity consideration also for open foundation, and check it from settlement consideration also. These two we have to check,